Hello, and a very warm welcome to today's Cell and Gene Therapy Insights webinar, titled New Methods to Separate Empty, Partial, Full and Heavy AAV Capsids. I'm Charlotte Barker, an editor at BioInsights, and joining me today is Aleš Štrancar, who will explore Sartorius BIA separations chromatographic columns that allow for batch-to-batch and scale-to-scale reproducibility. After the presentation, we'll have a live Q&A session, so feel free to pose your questions to our speaker using the Ask a Question box at the bottom of your screen, and we'll try to get to them during the session. I'd also like to draw your attention to the Resources tab on the right, where you can find more information on the topics covered today. So, to introduce our presenter today, Aleš Štrancar has been the Executive Managing Director of Sartorius BIA Separations since it was founded in 1998. He's one of the main inventors of the convective interaction media Monolith columns technology and co-inventor of many analytical methods, including methods for pDNA, mRNA, AAV, adeno, and other viruses. He is author or co-author of more than 100 scientific papers dealing with separation and purification technologies, and also co-author of several granted patents. So, without further ado, I'm going to hand over to Aleš to kick off today's presentation.
Thank you, Charlotte, for the introduction. Hello to everybody. Hope you will find some good data, some interesting information for your work. Before going to the topics, just a very short introduction of who we are. So, Sartorius BIA Separation is a part of a big Sartorius family. Our basically main area of work development are monolithic columns, which have been developed really for gene therapy purposes close to 30 years ago. The aim was to provide chromatographic media which is producing no shears in order to improve the recovery of shear-sensitive molecules, viral particles, and secondly also to enable better resolution, again for viral particles, nucleic acids, and also to provide better capacity for viral particles and nucleic acids. So this is really purpose-engineered chromatographic media. We don't have particles, we don't have sheets. It's always one single block of polymer, highly interchanneled. Today we offer a different type of columns. The most used would be simultus columns, which are basically packed in disposable housings. But these are multi-use housings, so you can use your resin up to the lifetime of the resin. Of course, you can also use it single. It's still not that expensive that you will not be able really to bear the costs of single use. We start with 1 ml, then we go 4 ml, and so on, 8, 40, 80, up to 40 liter. 40 liter is the biggest column we are able to provide nowadays. We can also provide you with 96 well plates, octet columns, analytical columns, and with our new program, HR, which stands for high reproducibility, all of these monoliths would be really of just the same property, of the same capacities, resolutions, and everything. So starting with 96 well plates up to the 40 liter, it will be always just the same polymer. Such kind of chromatography columns would allow you to improve your recoveries. With AAV, not that much, but if you are dealing with measles virus, you can for sure get at least 3 times higher recovery, better capacity, as I mentioned, and this is really lowering a lot your manufacturing cost. The other part of our products would be analytical, in addition to columns, monolithic columns, which can be connected just with every liquid chromatography system. We also provide our own liquid chromatography system, which we call PETFix. The PETFix is purpose-designed liquid chromatography unit, which allows faster method development and faster in-process control, but also more accurate in-process control. You can do analytics and small preps on the system. And we also have very big group of researchers, developers, over 100 of them which are dealing with process development. One of the projects we were involved in was to bring Solgesma to the market as fast as possible. So we are cooperating with Vexis. We are co-developing the purification process with them, and they're using our columns. Maybe worth to mention, this process is based strictly on ion exchange chromatography. No affinity resin is used, and proved to be useful, and as you'll see later on, also provides better recoveries. Yeah, if you now look to the adeno-associated virus manufacturing process, I will not touch the upstream, it will be the downstream. If we are lucky that our AAV can be produced extracellular, meaning most of the AAV itself will be out of the cell, then no lysis would be needed. Then the process which we suggest will be quite straightforward. So really, you should perform no lysis, no TFF, no freeze thaw before, because with this you avoid the formation of complexes, especially chromatin complexes. So if you really have such a sample, you just go to our first column, which is a hydrophilic interaction column, and on this column with the salt, you can perform size separation, not size exclusion, it is size separation. All the proteins, all the DNA will be in the flow through, just particles would bind. Then you elute the AAV and some other particles from the column. You take the fraction with AAV, you go next step. Of course, it can be affinity. Once again, we prefer cation exchanger because it provides better recoveries, and it's also cheaper and easier to scale up. And then the last step would be actually enrichment of the full capsid. This can still be done by ultracentrifugation. In addition to this, we have 3 different columns of 3 different modes. One is strong anion exchanger, QA, nowadays in a new product line with HR, which stands for high reproducibility. I will come to this later on. We also provide Prima S and Prima T, which can also work well with certain serotypes. If you are dealing with this process, downstream process, you should be able to see close to 80%, sometimes even more than 80% recovery of the AAV, full AAV, from the harvest to the pure full AAV. So very high recovery of the product. If you need to do the lysis, then things are much more complicated. On one side, you need to put much more efforts in process development. On the other side, recoveries would be lower because you need to deal with chromatin structures. So chromatin is a very big nucleosome. Nucleosome is formed by positively charged histones coming from the cell wall and negatively charged DNA. As soon as they hit in the liquid, they form a complex nucleosome, and this would grow. More time you do this cell lysis, more time you have DNA and histones together. Even you concentrate them, would be even worse. For more time, you allow this to make complexes, and these complexes would grow, maybe even to be bigger than half micrometer. This is usually one of the main reasons for the filter clogging, for the column clogging, for the column short lifetime. And it's not so easy to remove because some chromatins are more positively charged on the surface, some others are more negatively charged on the surface. They are of any size, so no chromatography is basically able to remove them all in one single step. So how would our process look when we need to perform cell lysis? We would first think about how to remove chromatin or how to prevent to make even more chromatin structures. So we basically go from the harvest to cell lysis. We try First, the salt cell lysis. Usually we would use half molar potassium chloride. If this is not providing good recovery, then we would maybe add some detergent, and maybe in some cases you go with just detergent. Why salt? Salt will partially prevent chromatin formation. After this, we would go to the next step, which is chromatin removal. We have several approaches for chromatin removal. It really depends on case to case, how the upstream sample looks like. We would use flocculation. We would use more standard TFF DNase treatment. We are now implementing another approach, which is solid phase extraction. But if the titer is high, if we really have nice productivity, we will just simply go to cation exchange column. You would need bigger column because you need to take into account that chromatins will stick to this column more than the AAV itself. So there will be competitive binding. So bigger column would be needed. Again, it is something which is part of the process development then to decide which way to go. Yeah, so the novel approach is solid phase extraction. We tried to make it very simple. We would provide gamma sterilized spheres, specially designed particles to be just thrown to the harvest. After some time, the chromatins would stick to the spheres, and then you can basically just filter everything through the filter and go to the next column. The next column, as I mentioned, usually in our case would be cation exchanger, which binds just any serotype of the AAV, any chimera. Even if you put something on the outside of the AAV, like antibodies or whatever, all this is going to bind on the cation exchanger. It's kind of semi-affinity ligand for the AAV particles. After single sphere, there would still be some nucleosomes present, which usually elutes before, and bigger chromatin structures sticks to this column very heavily. Even 1 molar sodium hydroxide would not wash them away. So the column will relatively soon be not performing anymore. Maybe you can perform 10, 20 runs. Afterwards, probably you would not do very long sodium hydroxide treatment, but you would probably change the column. Even under the AAV itself, if you go to the SDH page, you'll still see some residual histone bands, which means although 2 chromatin removal steps, which are quite powerful, there are still some residual chromatins left. When comparing the cation exchanger, as I mentioned, you can count on about 10% improved recovery. So maybe instead of 60% recovery from the harvest to the final formulation, you can probably count on 10% more, like 70%, if you use cation exchanger, because cation exchanger elutions and binding is much milder. You don't need to use very low pHs. And then the last step, which will be empty full. Here I'm showing more traditional empty full. Later on, I will show the improvement of this separation, where you can still see some chromatins in the final peak in the wash with sodium hydroxide, and we also perform here empty full separation. So how to now measure the removal of chromatin structures and nucleosomes? We developed a method using picogreen. So what we do, we inject the sample in which we basically throw a bit of picogreen. Picogreen sticks to DNA, all DNA impurities, and if we perform size exclusion chromatography, in this case, we are using 2 different detectors, UV, which may not be that sensitive. So the red is to 60 nanometer UV, the blue is to 80 nanometer UV. So the fluorescent detection is basically more sensitive. So whatever is under this fluorescent picogreen detection would be qualified as DNA impurities. So with CMOS usually we would remove about 90% of these impurities. We go further to cation exchanger. We further remove the stuff. There's still a bit of very big chromatins, but these are disappearing then after the final polishing with the QA. There is a genome here, and there is still some fluorescent signal due to the genome inside the particle. Nowadays, there is also maybe important to show infectious virus removal. We performed some study together with Regenerics. It was published in Process International 2 years ago. So the QA column not only separate or enrich the full, but also takes away virus particles, infectious virus particles for 2, 3, 4, 5 logs. And also you can remove 2 to 3 logs of endotoxins with this final polishing step. Now going further more to the analytics. So we could see lately that there are more and more, that there is more and more important to not only remove the empty capsids, but also the partials or the heavy capsids. So those which may carry on to the final products and fragments of host cell DNAs, and fragments of plasmids, or whatever. And this is why we tried to basically better understand how to remove not only empties, but also partials and heavies. Very powerful tool which we are using in our development is, as I mentioned, the PetFix. So it's a specially designed liquid chromatography station. One of the benefits of this station is that we can connect with this station many different detectors. In most of the cases, when working with particles, we would employ 3 different detectors. First being UV. In this chromatogram, the 280 is blue, the 260 is red. The AAV is basically detected or analyzed here by multi-light scattering detector, which is black. So the area here, although the sample is really the harvest, so quite dirty sample, the area of this peak here is quite nicely corresponding to the amount of AAV capsids, which would be in this case still full empty partial heavy. What about the protein removal and the DNA removal? If you would like to boost the sensitivity for DNA, we could already show before that we are using picogreen. In this case, the picogreen is used on the cation exchanger, so we can also see the removal of DNA-related impurities. And the second channel of the fluorescent detector we set towards the tryptophan excitation, so we can boost the sensitivity of the proteins, host cell proteins, and so on. So we have orthogonal method to just use a picogreen method or host cell DNA, PCR, and also to Bradford methods. This kind of set of detectors we also apply with our ultracentrifuge. So we run also ultracentrifuge. The most straightforward method when you get a new sample, you just put the stuff on the ultracentrifuge overnight, and the next day, with kind of a special apparatus, we are able to pump out in very uniform flow the material from the ultracentrifuge to the HPLC capillary directly to the HPLC detectors. So once again, we push the cesium chloride, in this case, slow down to push everything out through the capillary after, of course, centrifugation. So the white means the empties, the black here, or the blue is here, the full capsids. So if no column is used here, it is just really ultracentrifugation and running the material from the tube to the detectors, and then after detectors, you will even be able to put the fraction collector. So the material coming from ultracentrifuge would be starting here. So that's the material which is here. So then we push further the material. Next one to come out is the full bent, which we can trace with fluorescent detector. with the multi-light scattering detector and with UV detector, and then further down. And if we do a good job, the conductivity curve of cesium chloride should show us quite a nice linear peak. And this is exactly what we performed in real sample. This is AAV 9 sample, which was expressed in our labs. So the bottom of the tube, and then the material comes from the tube. So first heavy material comes out, the full AAV, some partials, not many in this case, and empties, and cesium chloride gradient. So quite nicely pumping out from the tube in uniform flow. So we have now the full peak coming from the ultracentrifuge. We also purified just the same sample with the QA column with our traditional method, and we collected the F, which is the full fraction, and we send this material to the Megadalton solutions. What we really liked is in their publication that they can separate capsids not only by mass but also by charge. So this is what they published. So this would be empties, very heterogeneous, partials also very heterogeneous, even fulls are heterogeneous, and some heavy material here. So this is now our SO3 elevate, which we then loaded on the ultracentrifuge and on the AAV QA column. And in our case, these are empties, these are partials, these are full. So every dot basically represents a particle. So we are dealing with very heterogeneous sample. And as you will see later on, it's not so straightforward then how to purify these things. So we took the material from the centrifuge, the fraction 2. Now we can debate a bit if we should collect a narrower band or whatever, but still, if we put this on the charge mass detector, we still see that the falls, of course, are still heterogeneous, but we still have some partials and even some empties. Either this is because of some shears in the ultracentrifuge, which maybe tear apart things, or that the travel of the full through the gradient is not so straightforward as we thought. We don't know. We were not investigating this. We did purification also on the column, and also on the column we see enrichment of the fulls, but still quite partials and also some empties. So neither of these two approaches is really resulting in like 95% full, almost that we would have almost no empties and almost no partials. So this is why we started to think how to improve resolution, and seeing this charge mass spec and seeing this very heterogeneous population, we came to the conclusion we need to do something to more unify the particles, the empties, the partials, the fulls, and by this we could be able to separate things better. And we indeed found some species which are perfectly okay, are CGMP compliant, which unify the particles, and by using these species, we can convert the separation of just the same sample, which is with our old method, usually performed with just sodium chloride gradient from 0 to 100 millimolar salt gradient. It would be pH, in this case, pH 9.0. So linear gradient, we see the empty in the UV, we see the full, the fluorescent we always like to have, because it's the best estimation of the ratio between the empty and the full. You don't need no calculations of extinction coefficients. And also we like to always have the multi-light scattering detector, because this gives us also an idea if there are some other potential particles in the sample. So we took just the same sample and we applied it to the new method, and we could indeed improve the resolution between the full, small amount of partials, and empties. So empties are now really baseline separated. I'm always showing linear gradient because linear gradient is most straightforward. If you do step gradient and try to show something in step gradient, you can easily show this separation far better. But nobody really knows how much of the empty is in the full and vice versa. So when we develop the methods, we always start with linear gradient, and then if the need be, because of manufacturing, because manufacturing could not like to use linear gradients, we can then turn this to the linear gradient. But whatever we do, we first use the linear gradient. So the fluorescent detector gives us an impression about the amount of fulls to 1% in this case, 63 of empties, a bit of partials, just a bit of empties, which are looking even later on. Can this be improved? Yes. Okay, so first, can this be scaled up? Yes, we need to scale up because we don't really have such huge amount of material. Keep in mind that we need to load on our 1 ml column something like E14 particles, even more sometimes, to really have a preparative run. So we were using just 1 ml unit here. The chromatogram looks quite the same. So to a certain extent, this is fully scalable. Then we took the fractions, we put them back on the analytical column, E1, under the fluorescent, most sensitive, really nice, empty, almost nothing else. And E3, the fulls, we still see some partials, especially here. The dPCR shows us 70-75% recovery of the product. I believe we can improve this with probably loading more material. So the purity in this case, by fluorescent detection, which at least for me would be the most accurate, would be a bit more than 90%. So we wanted to improve this, and with using the third species and performing dual gradient with 3 buffers, we can further improve the resolution. So now the empty is here, the partials basically move from here to here, and the full is here, and the heavy should be here. So we scale up this to, again, 1 ml unit, empties, partials, really long peak, and even the fulls are now divided, and some heavy here. So if we zoom in of this full peak, we can really see 2 populations of the full. So there is something to be done further here to better understand what are these 2 different, maybe even more populations in the full. If you now go to the HPLC, the fluorescent detector, if you take a look into the E2 and E3, both are really nicely purified. The fluorescent detection is really 99% clean, no partials, no empties. So with this, we can really enrich the full to be more than 99%. More important, we get rid of partials almost entirely, and we get rid of heavy capsids almost entirely. Yeah, of course, this can be done downstream, but sometimes maybe it's also good to think about the upstream. Can upstream help to improve the ratio between empty and full, and then to lower the amount of partials? Can upstream boost the expression of AAV? We wanted to bring, again, analytic here because we are quite blind what is going on in the upstream, and we know that there are many different parameters, from plasmids to transfection reagents, media, scale, suspension, not suspension, adherent, whatever. So a lot of different things may influence our expression. So how to better understand the upstream? We were designing the PetFix, we call it this one, switcher, which allows orthogonal chromatography. So our aim is basically to take the sample from the bioreactor or at any point of time, just acidify a bit the material, filter the stuff, and go directly to the system where we first capture the AAV. You usually would be loading about 5 milliliter of supernatant. So we concentrate the AAV here, and we also pre-purify the material. And then with the pH gradient, we bring just the AAV to the second column where we can perform empty full separation. And later on, we are also going to perform empty full partial heavy separation. So our idea is to make this completely automized. In the next step, also to have a probe into bioreactor and to just with peristaltic pump load the material on the first column and then run the chromatography. So first column is cation exchanger, which captures just any AAV. And with the pH gradient, we bring just the AAV to the second column. All the rest would go to the waste. If you look on the chromatogram on the first column, so this is the loading of about 5 milliliters of the sample. And then in very sharp pH gradient, we with very sharp peak elute the material to the second column. As soon as this is done, we clean the column and we regenerate the column to be ready for next injection. On the second column, in the meantime, we perform empty full separation, which is shown here. So in linear gradient, empty full separation, some residual impurities coming here. Sometimes we use also the size of this peak to better understand the amount of the impurities and cleaning of this column. So when the loading goes on, the analytics goes here. When we are basically eluting from here, then this column is under washing. So this we can do in kind of in parallel. So all these analytics just takes just 20 minutes and it's fully automized. For the better presentation further of what is going on, I'm not anymore showing the cation exchange chromatogram, will be just an ion exchange. But even the ion exchange chromatogram, I'm just going to show the part which shows the empty full separation. So zoom in on this part, which is in yellow. And I divide here the two chromatograms. The first would be with UV and the second with multi-light scattering detector. So if you inject the standard, we can estimate the empty full already with UV. Even if you have a nice expression, we can also use the UV to have an idea about empty full. But if we are at the beginning of the process or our harvest is not well optimized, the UV is not telling us nothing because the background is too high. So we need selective detector, which is multi-light scattering detector. And with multi-light scattering detector, we can still see the empty, the full, and even some other forms of particles. And now with this kind of methodology, we can start to basically study our process, the upstream process. The question here was, does the temperature influence our expression of the empty and the full? Is there a different ratio between the two? Is this influencing also other particles, which are impurities? In principle, no. We see nice overlap on the Mars detector. UV is just not sensitive, it's not selective, too much background. We always do the orthogonal method with PCR, so to see if the trend of the full with multi-light scattering detector goes the same direction of as with the PCR. But what about the ratio between the plasmid amount and the transfection reagent? Here we already see that there is a difference. So if you use the ratio lower, which means if you use less transfection reagent, we would produce the same amount of fulls but less empties. Then in the case we use more transfection reagents. So if you just use QA, we would basically see doesn't matter how much of transfection reagents are we using. But if you use this method, you will see you better not use such ratio because you only produce empties and more these other particles which are impurities. So the teaching here is let's really go for optimal amount of transfection reagent to not produce empties. Another factor which may also be important to check is the amount of plasmids per 1 million of the cells. Here we can see that using more plasmids per 1 million of the cell is only producing empties and these other particles. So it makes no sense to use more plasmids. It's also more expensive. Keep an optimal amount of plasmids per 1 million of the cell. And also you can go further and perform many other tests. You can also do your kinetics. So here we took the chromatogram at the beginning of transfection, so the fluorescent is flat. Also the multi-light scattering is flat, and then over the time we see both the full and the empty to grow. If you now plot the full, we would see that basically, usually in most of the cases, 2 days are enough to produce the full, because after 2 days you mostly produce impurities. So very few cases needs 2.5 days. Usually, at least in our hands, most of expressions would need about 2 days, and then you should stop. Once again, after this, you produce a bit more empties, and you also produce other impurities, and also your equipment. You can imagine 1,000 liter bioreactor, also the costs to run something for nothing. Yeah, so these are the tools. We have been a lot criticized regarding our batch-to-batch, scale-to-scale reproducibility. I need to say that we were qualifying our columns from the very beginning with small molecules, because you should not introduce on the CGMP compliant column something which is organic. These small molecules we found later on are not representing the column properly. So we did a big study, we plotted ion capacity of each of our column, different sizes, and tried to see at which amount of salt we would elute the empty capsid, AAV capsid, and you see there is just no correlation. So when we started with these applications 10 years ago, we were basically always working with linear gradients. So if there is a difference in the column performance or difference in the buffer preparation, both peaks, empty and the full, moves left or right. Resolution is maintained. But of course, if you try to put step gradient, then it must not move anymore. We need to make sure that buffers, that columns, and all the other stuff is properly optimized such that your valley between the two peaks is always on the same spot. So the only way to realize or to provide such columns was to start to qualify the column, not anymore with ligand density using small molecule, but with AAV itself. And that's just the only way we tried within the last 5 years, many different things. And just the only way is do it with AAV. Only AAV will tell you the performance of the column for the viral particle. No small molecule, no protein will be able to predict the column behavior. So how to do now this with CGMP compliant columns? We basically cut a ring from the monolith from the top and the bottom before we mount it to the housing and pack the column. And we decided, kind of similar to porous particles, where we take a small sample after the big batch of particles. We took a small specimen, we cut it from this ring, the bottom and the top, and we put this specimen into a small housing. And now here we run the separation of empty and full. And if you would see that the separation fits to certain criteria set, then we would say column is okay, we would sell it. Otherwise, we would throw it. So that's a new method we implemented. Of course, we had to prove that the disk from the top and the disk from the bottom are representing the complete column. So what we did is we took the disk from the top, from the bottom. We were running in the linear gradient empty full separation, empty capsid eluted at about 91 millimolar sodium chloride. Then we packed the housing with the monolith. We ran just the same separation on the 800 ml, of course with small amount of the empty and full AAVs. We are at quite the same. amount of the salt in linear gradient needed to elute the empty capsid. And then we took the monolith out, we cut it to further rings like ring K, B, and C, and we also qualified this disc, or we checked this disc for the elution of the empty capsid, and we also see that it is basically within the acceptance criteria. So with these three checks, and with this also with other sizes, other columns, we can prove that the monolith is really very homogeneous, because as you will see later on, we are going and we are already releasing these HR columns within the plus minus 3% of the salt which is needed to elute the AAV8 empty capsid, which we produce ourselves to qualify the columns before released to you. So we checked the method, also scale to scale, 1 ml, 4 ml, 8 ml. I need to point out that the housing here are changed. We had to fix that volume of the housing to fit to bigger units. So we check smaller units as they are, as a column. They are not CGMP. The bigger unit being CGMP, we only test the specimen. And if you now overlap everything and plot everything with the salt gradient, you would see quite nice overlap of the valley between the empty and between the full. So this is now at least 10 times better reproducibility of our columns scale to scale, batch to batch, and should really now allow for linear or for step gradient elution. So if you now put your step here, you will be really within few percent. Doesn't matter the size of the column, doesn't matter the batch. You will be within 3% plus minus salt, which is, to my opinion, with new method which we are introducing, which allows better separation between empty and full, far than good enough that you can have very robust manufacturing of the full AAV. So the release criteria at the moment with this batch of AAV, which we produce, is 92.3 millimolar potassium chloride plus minus 3%. So if the column fits to this, we'll sell it. Otherwise, we throw it. So we are throwing about 50% of the columns because of this, and this is why the columns are 40% more expensive than our traditional SimQA material. So all of this is now going to be SimQA HR, and the next step will be Prima S HR. So we'll start to provide all of our chemistries, or at least important ones, also with HR programs, meaning they will be qualified with viral particle. Yeah, to conclude, we believe that at least it works to test to compare the affinity capture with cation exchange capture and see what the recovery would be. Pay attention, the recovery you need to check on the second column, because if you destroy your particle on the affinity, the PCR will still show you very nice recovery, but the centrifuge later on will show you that some of these particles are destroyed. The PETFix which we put together, we believe it's very powerful tool for process development, for in-process control. You can also use it for product release tests, but really the primary goal of this machine is to provide much faster process development. The new methods which we're implementing with some novel species in the buffers provide 5 to 10 times better resolution in comparison to our old methods. It works with any serotype. Mostly I was showing you AAV8, but it works with just any serotype, at least those which we tested so far. And yeah, with the novel generation of our HR columns, we believe that the enrichment of the full AAV capsids and also adeno capsids and also some other capsids will be far more robust than it was the case until last month when we introduced this our stuff to the market. Last but not least, we are running every second year summer symposium, which is emphasized on the monolith, but usually there are a lot of different talks about manufacturing of nucleic acids and manufacturing of any viral particles. And we are still collecting abstracts, so if somebody would like to present, most are welcome. You are also much welcome to just join the event. We usually have some very knowledgeable and some very experienced presenters working in industry for quite some time. So it's also a good place for networking. And we have very good wines in our region, and some food experience would also be nice, I would say. With this, I would like to thank you for your attention, and I'm very happy to take your questions.
Wonderful, thank you, Aleš. We're going to start our Q&A now. So if you'd like to turn your camera on, that would be great. And yeah, I'm gonna give you some questions here. So first question I've got here, can you please explain a little more about the 2 mobile phase chromatography?
We filed some patents about this, so we don't disclose these things. We have been advised by our patent lawyers not to disclose these things until this is published. But we have special kind of possibility. We can work through the project, and in such case, the things would be disclosed. So if somebody is interested in this, let's get in touch, email after the presentation, and we will find a way to basically give you the insight of these methods sooner than they are published, and they will be published second half of next year.
Brilliant. So viewer, we'll get in touch with you. We've got your email, so we'll get in touch with you offline. Brilliant. Next question I've got here. Would it be possible to achieve reproducible purification of AAV full capsid using QA/HR, even if the step elution is used?
Yes, with the new methods even more, but even with the old methods, without using these special species in the buffers, yes. It would be, I would say, 5 to 10 times more robust, more reproducible scale to scale and batch to batch than it was so far.
Brilliant. If anyone else has questions, we've got a few more minutes, so do send your questions in. If we don't get to them today, then we will try to reply by email anyway, so you should get your question answered either way, so do keep them coming in. Another one I've got here, is QA/HR already available to purchase in all sizes? Are there also CGMP columns, and what's the delivery time?
Yeah, the small ones are available from stock. The big ones would be up to 6 weeks, the same as with all our other columns. So they were basically released officially end of October, and yeah, now we have them available.
Brilliant. Got someone here, I'm not quite sure what they're asking. They say, what about the QA elution buffer component? So I guess they're just wanting a bit more information on that.
Yeah, here I would just basically repeat the same answer as with the first one. We can maybe discuss offline these things and find a way how we can disclose the things sooner than end of next year.
Okay, brilliant. Have monoliths already been used in purification process of any commercial gene therapy products?
Yeah, one of them I showed in one of my slides at the beginning. It is Zolgensma. Zolgensma is produced using our column. And as I said, it's not affinity process. It is based on ion exchangers. So affinity, at the time, ion exchanger proved to perform better.
Okay, this might be another one covered by patents. I'm not sure. Can you share any information about the buffers used in the new separation method?
There would be a way, yeah, but let's discuss this via email and find a way how this can be exchanged.
Perfect. Why would you think that it's possible to achieve better AAV purity with monoliths compared to resins?
There are probably two reasons. First reason is that in monolith you have only laminar flow through the complete column, which means there is no mixing. Between the porous particles you have some void volume and you have some eddy diffusion, and we know that eddy diffusion basically works against resolution. And second reason is monolith has no dead end pore, and dead end pore also is kind of lowering the resolution unless you run your process extremely slow.
Okay, brilliant. Thank you. That makes sense. I think we've got time for one more question, maybe. Is there a difference in purity and recovery when comparing performance of traditional QA with the new QA HR columns?
Oh yeah, sure, because you are now able to be more precise with the step gradient. You can improve the recovery, I would say, of the full. You would basically be more robust, so you can, because if the column or the buffer preparation is not robust enough, you probably would sacrifice a bit of full not to have too much empty in the full. So because of more reproducibility between the columns, you can, in principle, improve your recovery because you don't need to be that picky to be on a safe side to get rid of the empties.
Okay, brilliant. And just I guess a bit of a follow-up on that, but generally, what is the yield between monolith versus resin?
With AAV, we proved, we have a white paper on this. If somebody's interested, we can share. We proved 10% better recovery using the, I would not only say because of monolith, but because of cation exchanger instead of affinity. I would say that there is probably the better recovery with cation exchange monolith is due to the cation exchanger plus due to the monolith itself. And probably more due to the cation exchanger because we don't go that far with low pH.
Brilliant. Thank you very much, Aleš. I think that's all the questions we've got time for today. Any questions we didn't get to, we will reply by email. The webinar will be available on demand tomorrow, so look out for an email from us with the link. And I think all that's left is to thank Aleš once more for a great presentation, and thank you to the audience for listening. We do hope you'll join us again soon.
Thank you all, and keep in touch.